Welcome back, friends, to our AI A to Z series. Why do we build AI? The point is to use it, right? The fancy word for this step is AI inference. I'm Dr. Sonali Tamankar, and today we have AI for the pragmatic. I is for inference. Imagine someone taking out a whole bunch of student loans and going to medical school. Training or building AI is a similarly big investment. We talked in F is for foundation models, how especially in the generative AI age, this requires a lot of compute and energy. Inference is where all this training is put to use. When you type in a question and Copilot gives you an answer. This is like a trained doctor diagnosing the patient in front of them. Now, medical school is a one-time intense investment. This training may take 10 years. Diagnosing the patient may take 10 minutes. But a doctor is going to spend the rest of their life diagnosing and treating patients. Similarly, energy usage and climate impact of AI inference can dominate at scale. Let's look at a few examples of inference in general. In D is for deep learning, we talked about different kinds of AI applications. When you set your room thermostat to 68 degrees, the heater kicks in as soon as the temperature drops below this setting. This is the simplest rule-based inference executed by a simple logic gate and takes almost zero power. It happens right there on your wall, technically called edge computing. An example of machine learning would be when you swipe a card at the grocery store. Your bank has trained a machine learning algorithm to detect fraud, and this is the moment of truth. Should it allow your transaction to go through? This is a cloud-based inference. Your data is sent to the bank, which gives a thumbs up, and the checkout clerk hands you the receipt. This has to happen relatively quickly, or else a long line will form behind you. Sometimes this inference latency is even more critical. Imagine an automated vehicle realizing 2 seconds later, oops, I should have stepped on the brake and not the accelerator. Next example, you take a picture on your phone and then an app on your phone tries to decide how many calories are in your meal. This requires deep learning and specialized hardware like neural or tensor processing units on your phone. Quite a step up from the simple logic gates in your thermostat. If you want a long email summarized, you need generative AI. Now we are talking about sending data on the cloud to big shared GPU clusters, and then they will send back the answer. You might worry about privacy if this message contains personal information. The company hosting the GenAI model has to worry about throughput, as it is receiving a ton of requests at the same time. If you subscribe to a paid service or use an API, you worry about cost per token. So all inference is not created equal. There are many considerations that must be taken into account, like latency, throughput, power, size, cost, privacy, and more. In fact, inference time constraints are part of the problem statement in designing AI systems in the first place. Now that we are in the age of LLMs and vision models, which have giant memory and compute requirements, people are increasingly talking about LLM serving and looking for ways to make these models smaller. Miraculously, it turns out that it could be possible to make them much smaller, even by a factor of 10, without significantly losing accuracy. A 2018 MIT paper called this the lottery ticket hypothesis. If you know exactly which parameters were the lucky ones, you could use a much smaller neural network. Let me give you a rapid fire tour of a few key ideas how this is done. One approach is called optimal brain damage. You drastically prune the neural network while still maintaining accuracy. Another approach is factorization. So this is where you replace, say, 100 times 100 parameters or 10,000 parameters by 100 plus 100 or 200 parameters without decreasing accuracy and while reducing the memory requirement drastically. If you have visited sites like Hugging Face, you've probably seen quantized models where you get rid of a lot of decimal places, again, without significantly compromising accuracy. Yet another method is called distillation, and this is a bit like Cliff Notes. You train a big model first, like the original novel, and then train a small model to mimic what the big model does. Companies are also constantly pushing limits on both hardware and software for faster inference. Microsoft and NVidia announced in November 2025 that they set a new inference record of 1.1 million tokens per second. I'll put a link in the description below. So we are working hard to make inference as efficient as possible in artificial intelligence. Now, how does it compare with natural intelligence or our brains? In terms of power efficiency, there is absolutely no comparison. Our brains win hands down. If our brains were as inefficient as AI, we would have to eat something like a burger every second to function. Now, depending on the assumptions, the exact calculation may differ, but it is undisputed that our brains are far more efficient. I'll link a paper below to extreme edge computing for wearable devices. Their goal is highly efficient inference and even some training right there on your device using neuromorphic computing. One reason why our brains are so efficient is that they idle when nothing is happening and only compute when something changes. Spiking neural networks or SNNs try to replicate this behavior. Another smart thing the brain does is that it has data and compute in basically the same place, so there is no shuttling of data to the processor for computations. This co-location is another way to save energy. The brain also blurs the boundary between training and inference, like a doctor continually learning as they treat patients. Researchers are trying to create algorithms and systems and devices with such capabilities. So, quick conclusions. We talked today about how training is a one-time huge investment and inference is incremental. We discussed different kinds of inferences and ways of optimizing them, and how in the future we may see more edge inference and neuromorphic technology. Very practical topics today on how to use all this AI. Tomorrow, we have a provocatively titled topic, AI for the Anarchist. Hope you can make it to discuss guardrails and jailbreak. See you then, and bye for now.